So in the reaction type category, single replacement has for a description, the element takes the place of one part of the compound. So in single replacement, the element takes the place of one part of the compound. What you'll see is this. You'll start with one element and one compound, and you'll finish with one element and one compound. Now that doesn't mean it's the same exact substances. It will be a different element and compound at the end than it was at the beginning. But the key thing is the element takes the place of one part of the compound. So that's why it's called replacement. The element is going to replace something that's in the compound. So to identify single replacement, what you're looking for is on your reactant or your product side, one element and one compound. And that's how you'll know that's the type of reaction that should be occurring. Now in the first example, the sentence says copper metal reacts with silver nitrate solution. All I know are the reactants, much like what we did yesterday where we're predicting one side of the reaction. So we'll start by writing the formulas that go with that sentence. Copper metal is Cu solid. I know that it's solid because it's all by itself, and according to my periodic table, it is a solid. The fact that we use the word metal would also be an indicator that we're talking about something that's solid. It reacts with something, so I'm going to put a plus. Remember, that means that I can put different coefficients on each of them. And I'm going to have silver nitrate solution. So when I have a compound, I care what the charges are. Silver is +1, nitrate is -1. Nitrate is a polyatomic ion. I know that, in part, because it ended with ATE. If it ends with ATE or ITE, it's definitely a polyatomic ion. Since they both have the same charge but opposite sign, I know that I need one of each of them. So the formula is AgNO3. And since solution is the state, I write AQ. AQ is the state when I've dissolved something in water. Now that's all I know so far. So I need to predict what the products would be, understanding that this is a single replacement reaction. And again, I knew that because I have an element and I have a compound. So the description says the element takes the place of one part of the compound. So this is my element, and it's going to replace something that's in the compound. How will you decide? Well, copper is a metal. Silver is a metal. It makes sense that a metal would replace another metal. If you tried to replace the other side of the compound, you'll notice the charges won't balance out. You'd end up with two things that are positive and it won't work. So that could be a clue that you need to go back and change what you're doing. So the idea here is that copper is going to replace silver. That means that at the end, silver just got bumped. It's not in the compound anymore. Copper replaced it. Silver is now all alone. When silver is alone, it's a metal, it's a solid. Copper took its place, so copper will now be in the compound where silver was. Now, whenever you make a compound, you must consider the charges. So I cannot just write CuNO3. I have to think, what's the charge of copper? When I look on the periodic table, we'll see that copper has two choices, 2 positive or 1 positive. And this question came up yesterday, and the answer is, when we don't say which charge to use, it's the first one. That's the more common one. And by first, I mean the one that you read first. We read from left to right, so the one that's on the left would be the one that we choose. That tells me copper's charge is +2. Since nitrate's charge is only -1, that's not balanced. I could use swap and drop, and I would discover that I need 2 copies of nitrate. Now, I haven't written the state for this yet because I'd like to pause there and ask, does anyone have any questions so far? So now for the state. You'll notice that in replacement reactions, very often we are dealing with solutions. It's very common. So if I have a solution at the beginning, that means that there's water around. I could have a solution at the end as well. So when I think about my ionic compounds, which are sometimes soluble in water, I'm not going to immediately say that that's a solid. I'm going to ask myself, is that compound soluble? Using my solubility table, I'll see that, yes, copper 2 nitrate is soluble. In fact, everything makes a soluble compound with nitrate. So I would write AQ, indicating that that compound is soluble. So the idea is that if I have a solution, and I know I do, it said that I had a solution, when I'm writing ionic compounds, I have to check now, are they soluble or are they not? Now for the balancing, you could, if you felt like, consider nitrogen and oxygen, which make up the nitrate polyatomic ion, as one group. That's what I'm going to do. On this side, I have one of everything. 1 copper, 1 silver, 1 copy of nitrate. On the other side, I have 1 copper, 1 silver, but 2 copies of nitrate. So the first thing I need to do is balance my nitrates. I'll do that by adding a coefficient 2 right in front of the compound silver nitrate. Now I have 2 nitrates, but I also have 2 silvers. So I need to adjust the other side as well, so that I have 2 silvers on each side. So we're still going to practice balancing, but in the context of different types of reactions. Would anybody like to ask any questions about this example? So then my second example is to show you what happens when the element is a nonmetal instead of a metal. So it's the same kind of reaction, but it'll be a slightly different scenario. In the second reaction, oxygen reacts with magnesium chloride. So our first step will be to write out the formulas for oxygen and magnesium chloride. Oxygen, we know from previous lessons, is O2, and it's a gas. Magnesium chloride. Well, magnesium has a charge of +2, chloride ions a charge of -1. So when I write out the formula, I would write MgCl2. Now here, I didn't say that there was a solution. When there's no solution possibility, the rule is that ionic compounds are solid. So we would write an S. Now I need to predict my products. Now the description, let me remind you, says that the element takes the place of one part of the compound. Oxygen is my element, magnesium chloride is my compound. So oxygen is going to replace part of the compound. Oxygen is a nonmetal. So is chlorine. Oxygen will replace chlorine because they're both nonmetals. Oxygen will not replace magnesium. Magnesium is a metal. So they've always got to trade places with something that they are similar to. Metals with metals, nonmetals with nonmetals. That means that oxygen is going to come and replace chlorine in that compound. That means that at the end, chlorine is now going to be all alone. When chlorine is alone, it has a 2, and its state is gas. When oxygen, which has a charge of -2, goes together with magnesium, which has a charge of +2, we see they have the same charge but opposite signs. That means we need one of each of them. So I would write MgO. I'd also say that it's solid because ionic compounds are solid unless we say that we've dissolved them in water. Now our last step is to balance. So to balance, we count things out. I have 2 oxygens, 1 magnesium, 2 chlorines on this side. 1 oxygen, 1 magnesium, and 2 chlorines over there. So I can see right away that it's my oxygen that's out of balance first. My solution will be to put a 2 in front of magnesium oxide. Now that will fix oxygen, but it will also affect magnesium. Now I have 2 magnesiums on the product side, only 1 on the reactant side. So I'm going to have to add a 2 here. Now I have 2 magnesiums on the reactant side, but I now have 4 chlorines. So I've got to make one more change. Put the coefficient 2 in front of chlorine. Now I have 2 oxygens, 2 magnesiums, and 2 chlorines on each side of the reaction. So of the things that were new and different, the key is that in single replacement, you have 1 element and 1 compound, and the element replaces one part of the compound. Would anybody like to ask any questions about these 2 examples? So we're also going to talk about double replacement, which is almost exactly the same thing with just a small change to it. Before I go there, does anyone have any questions they'd like to ask about these 2? So we're just going to do one example of double replacement because it's essentially the same thing. The description for double replacement is 2 compounds exchange elements. So 2 compounds exchange elements. If I was to write what I have in a double replacement reaction, I have compound plus compound giving me compound plus compound. So unlike any other type of reaction we've seen, there are no elements that are all alone in double replacement. So in double replacement, 2 compounds exchange elements, and we'll follow the same sort of rules as we did for single replacement. So we'll start by writing out my 2 reactants. It says that I have zinc sulfate solution mixed with ammonium chloride solution. So first step, think about charges because I'm making compounds. Zinc is 2 positive, sulfate 2 negative. Ammonium is +1, chloride ions are -1. Notice how I wrote down all the charges with the question. I did that on purpose because I'm going to need them more than one time, and rather than having to look them up again or go back or rewrite things, I just jotted them all down here. That means when I write zinc sulfate, I would write ZnSO4. Since they both have the same value but opposite sign for their charge, I only need one copy of each of them. Since it says solution, AQ. I'm mixing it with, so there's my plus sign, ammonium chloride. Now remember, ammonium and ammonia are not the same thing. Ammonium is a polyatomic ion, NH4. Since ammonium and chlorine have the same charge, I need one copy of each of them. This is also a solution, so I write AQ again. Now those are my two reactants. Notice how I have a compound and a compound. That's how I know this is double replacement. I have two compounds. Now it says the two compounds are going to exchange elements, and they're going to exchange them pretty much the same way we did in single replacement. Let's consider these two pieces. They are both cations. Notice how I'm referring to them as whether they're positive or negative, because now they're all in a compound. The cations will trade spots. So in the end, zinc will go over here, and ammonium will go over there. So the result will be zinc with chlorine, sulfate with ammonium. Yes. You could imagine that it's the anions that are exchanging. It would be exactly the same thing. I like to pick the cations because they're first. But honestly, you could say that sulfate and chlorine are changing spots, and you would get the same exact answer. Easton, do you have a question too? Mm-hmm. So on single replacement, I'll just back up and then come right back here. The element here was a metal, so I had to switch it with the metal in the compound. In the second example, the element all alone was a nonmetal, so I chose the nonmetal portion. So I'm always switching like atoms. Metals with metals, nonmetals with nonmetals. So back to double replacement. The cations are going to switch spots, or if you want to think about it like the anions are switching spots, go ahead. You will get the same thing. At the end then, I have zinc chloride, and I have to think about charges. Remember, zinc is +2, chloride ions -1. So when I swap and drop, I will end up with ZnCl2. My other compound is ammonium with sulfate now. Ammonium is +1, sulfate, like we said, is -2. So when I swap and drop, that tells me I need 2 copies of ammonium. That means I need brackets with a 2. And my formula would look like that. So when you're making compounds, consider the charges always. Now for the states. I had solutions at the beginning, so I should check, can my final substances be solutions also? Using the solubility table, I will find that both of those substances are soluble. And so I would put AQ as the state for both of them. Now my last step is to balance. For some reason I decided not to write oxygen here, so I'll add it. Now when we're balancing, we can consider the polyatomic ions as if they were one thing, or we can count the atoms individually. I like to consider them as one thing, so I'm going to say I'm going to count sulfur and oxygen together, and I'm going to count nitrogen and hydrogen together, because those are my polyatomic ions. So on the left, I can see I have 1 zinc, 1 sulfate, 1 ammonium, and 1 chlorine. On the right, I have 1 zinc, 1 sulfate, 2 ammoniums and 2 chlorines. So it's ammonium and chlorine that are not in balance. This is actually a simple fix. If I put a 2 in front of ammonium chloride on the reactant side, now I will have 2 copies of ammonium, 2 copies of chlorine, and I'll be in balance. So single and double replacement are very similar. The difference is in double replacement, I only have compounds. In single replacement, I always have one element and one compound. Is there anybody who has questions about this example here of double replacement? So we got one more type. And the one more type is combustion. Now combustion is all on its own because it's different than the other types of reactions. In combustion, you will have a hydrocarbon reacting with oxygen to produce CO2 and H2O. So I'll give you a bit of description here. A hydrocarbon reacts with oxygen to produce CO2 and H2O. I'm pretty sure that you know what 3 of those things are. Just so that you're clear, a hydrocarbon is something that has some amount of carbon and some amount of hydrogen. I put X and Y there because the numbers can be different. But a hydrocarbon is something made out of carbon and hydrogen. So in a combustion reaction, a substance that has carbon and hydrogen will react always with oxygen. And you will always produce CO2 and water. So you don't have to guess what the products are here. It will always be these substances. So when we write a combustion reaction sentence, there's very little words that are actually going to show up. The word that I want you to highlight here is the word burning. Burning is your clue that it is combustion. Your other clue is that there's nothing else mentioned. You get the name of one substance and what's happening to it. In this example, I give you methane. Methane is one of those molecular compounds whose name is not necessarily based on prefixes. The formula for methane is CH4, and it's a gas. So like water, like ammonia, that's a formula that you just kind of have to know. Now that part you actually had to put in, but the rest of it won't ever change. In a combustion reaction, oxygen will always be the other reactant. Oxygen is a gas. In combustion, CO2, which is a gas, and H2O, which in the case of combustion is also a gas, are always the products, always. So you don't have to guess, you don't have to predict. You just simply have to know and remember that in combustion, these 3 pieces are always there. The only thing that's different is the first substance. So when you balance a combustion reaction, notice that oxygen is all over the place. I recommend that you always do oxygen last. Even if it seems like there's a lot of them and you should try balancing it first, don't. Balance the other 2 substances first, then balance oxygen. So the general rule of thumb is to look for your biggest number. On the left, I have 1 carbon, 4 hydrogens, 2 oxygens. On the right, I have 1 carbon, 2 hydrogens, and I'm not even going to think about oxygen yet because I'm going to end up changing the number a few times. So When it's a combustion reaction, just ignore oxygen in terms of balancing until the very end. If I think about hydrogen, 4 on the left, 2 on the right. So if I put that coefficient 2, now I have 4 hydrogens. That is what I wanted. Notice how as soon as I did that, it changed the number of oxygen. I knew it was going to do that, so I didn't even bother counting oxygen to start. I have 1 carbon on the left, 1 carbon on the right. That's great. I don't need to put a coefficient anywhere to balance that. Now I'll consider oxygen. In total, I have 4 oxygens. 2 here and another 2 there. So don't forget that in combustion, oxygen is part of CO2 and it's part of water. That means that on the left, if I put this coefficient 2, I could have 4 oxygens there as well. So this number should be the last one that you add. So you shouldn't be adding a coefficient in front of oxygen until you've balanced all of the other atoms. Now in the next example, it's a different hydrocarbon, and it's one whose name I wouldn't have expected you to have known. So the lucky thing for you in combustion is that you don't usually have to write formulas. You just have to know which substances belong in combustion. If this was a test, I would tell you that pentane is C5H12. I wouldn't have expected you to know that. It's a liquid. I would expect you to know that when I say the word burn, I mean combustion. So that means oxygen gas is a reactant, CO2 gas and H2O gas are products. So notice with combustion, there's really no tricks. You just have to remember those 3 pieces of the reaction. To balance, I'll count. On the left, I have 5 carbons, 12 hydrogens, 2 oxygens. On the right, I have 1 carbon, 2 hydrogens, and I'm not even going to count oxygen. I'm going to leave it till the end because I know it's going to change. We'll start with hydrogen. There's 12 on the left, 2 on the right. So if I add the coefficient 6, 2 times 6 is 12. Now I have 12 hydrogens on either side. For carbon, there's 5 on the left, but only 1 on the right. So if I add the coefficient 5, now I have 5 carbons on either side. Now that I've done that, I'll count up how many oxygens I actually have on the right. 5 times 2 is 10. 6 times 1 is 6. Altogether, that makes 16 oxygens. And so my last step should always be putting a coefficient in front of oxygen. If I put the coefficient 8, I will end up with 16 oxygens on the left.